then taking subjects which are of 2 and 3 credits would be affected, right? So in those situations, things are dynamic in nature. Things are dependent on the choices I make. If I select a subject of 4 credit, then I probably can take just 2 more subjects which are of 4 credit. If I select a subject of which is of 3 credit, I can take 3 more subjects which are of 3 credits, right? So stuff gets dependent. It's not static, it's dynamic in nature. So that's the most basic way in which you can understand if a problem can be solved using dynamic programming. So there are multiple typical kind of questions which are always solved using dynamic programming, and three of those are going to be covered in CS146. Those are finding subsequence and cutting rod cutting problem, as well as 01 knapsack. So these are the typical problems which you need to understand in order to go out there and try real world scenario problems on websites like LeetCode and HackerRank. So so that's like the basic gist of what dynamic programming is, that whenever you're in a situation where making one choice can affect the other choices you can make, it probably can be solved using dynamic programming. But why we always don't solve using dynamic programming is because more often than not, the tables we are forming, so dynamic programming is kind of like a 1D or 2D matrices that we are filling up. Okay, so these are kind of lookup tables that we form in order to make our programming faster, but it has a downside that there might be in certain situations methods which are faster than dynamic programming, because more often than not we end up making a 2D matrix in dynamic programming, which means we are more often than not doing a O of n squared algorithm. But it's better than having some 2 to power n, right? So if we are in a situation where the other solution is leading us to like 2 to power n solution, then it's better off to have a solution which is n squared. But if you have a solution which is n squared in dynamic, but you have a better approach iteratively or recursively, then probably those will be the better approaches. So the question comes, how can you be absolutely sure that a problem can be or should be solved using dynamic programming? So my 2 cents on those would be that there are 2 ways in which you can know that a problem can be solved using a dynamic programming. So whenever we are in a situation when we have uh, when the problem doesn't have optimal substructure, and whenever we are in a situation when we are solving the same problem or just a part of it again and again. So what I mean by that is, we can imagine the scenario of calculating Fibonacci. So as you guys might remember, when professor was teaching this in class, he explained how in order to calculate Fibonacci of 5, we need Fibonacci of 4 and 3. In order to calculate Fibonacci of 4, we need Fibonacci of 3 and 2. And in order to calculate Fibonacci of 2, we need 1, right? So you realize that in order to do all that, you are calculating Fibonacci of 3 twice, you are calculating Fibonacci of 2 twice, and Fibonacci of 1 twice, which is 1. But you are calculating a lot of stuff again and again redundantly, right? This was just when I was trying to calculate fib of 5. What if I was trying to calculate fib of 100? And what if I was trying to calculate fib of 1000? That would mean that I am doing some work again and again, which is already done. So the logical way of approaching this problem would be that I can probably store these values, these intermediate values, in a lookup table and go to those values whenever they are needed. For example, I start from 0, I calculate fib of 1, I calculate fib of 2, and keep on storing those values, unique values, in a table. And whenever I need a number, let's say I need to calculate fib of 6. I have fib of, so in order to calculate fib of 6, I need fib of 5, 4, 3, 2, 1, and 0, right? I'll need all of those values. So in order to calculate, I don't need to recalculate those. I already have those in my lookup table. So that saves me a lot of space, a lot of time, but it takes up some space. That's the trade-off we always need to do, right? Space and time complexity. So we always cannot have both the things. So the trade-off here is that I'll be using some space in order to save those intermediate values, but the positive part is that I get speed, because if we take extremely large values, which are possible in industry situations, when we work out in the industry, in such situations, if we go with the regular approach, the solution might take even longer than we'll probably live. I've seen problems in bioinformatics where if you solve it for like 5 seconds, if you solve it for like 5 records, it takes like 10 seconds. But if you solve a sequence for like for 10 sequences, it takes a million seconds, which is a lot of time, right? So that is why you need to realize when you're solving some questions that whether the time complexity is some number to the power n, or is it just n square or n cube or n, what's the time complexity. The second thing you need to see is, can it be approached using dynamic programming? And when I say dynamic programming, it's simple. As I said, can I can you find something which you have already calculated? Is the problem having some part which is already being calculated again and again? And can you break the problem into some very optimal substructure, like very basic problem which needs to be solved, and you attack just that part of the problem, and once you have solved that part of the problem, you're done. Trust me. So the another amazing part about dynamic programming is that more often than not, in 90% cases, the number of lines of code you are required to write for a dynamic programming problem is less than 5. It's mostly 1 to maximum 5. And that's the beauty of dynamic programming, that you do all the work in minimal lines of code and while having the speed up. So that was a brief intro of how dynamic programming can be used, what dynamic programming is, and how to approach and how to think when you are given a problem, that whether it can be solved using dynamic or whether it should be solved using iterative or recursive solutions. And now Raj will cover a bit of rod cutting problems. So Raj, I'm feeling a little bit confused. What is this rod cutting problem? Can you please explain this to me, please?
Sure. So um, the rod cutting problem. You're given a rod of length n, and you're given an array of values where for a smaller piece of the rod you're given a price. So let's say, for example, the array contains values 1, 3, 5, and for 1 you have a price of 5, for 3 you have a price of 10, and for uh, so basically, for each smaller piece of rod, you're given a selling price. And the problem that you're supposed to solve is, given this rod of length L or N, find the maximum price you can sell it by cutting it into smaller pieces.
Mm-hmm. Okay. So I think what I could understand from what you said was that I am giving certain costs for certain lengths of the rod I can sell it in, and you will tell me a total length of the rod, and then I need to make maximum profit by selling that rod. Is that right?
Absolutely.
Okay. So all the other participants or all the other people who are watching this, this is what rod cutting problem is. That you are giving certain pieces. Let's assume this, like you are a shopkeeper and you have a rod which is of length 1. You can sell that for $2. You have a rod which is of length 2. You can sell that for $4. You have a rod which is of length 3. You can sell that for $5. You have a rod which is of length 4. You sell that for $3. Okay. So now your boss comes up to you and tells you, okay, now you sell a rod. I give you a rod. It's 10 inches long. Cut it and sell it with maximum profit. Now you are a human. You can calculate this, and mind you, even after being human, it will take you around 5 or 6 minutes to try all the possible combinations or even longer to check what would be the maximum price or profit that you can obtain from this problem. Imagine this problem to be solved by a computer. A computer doesn't know that, okay, if I'm selling this for $2, okay, $3 is greater than $2, I can probably achieve more profit by doing that, right? We need to tell computer, we need to write an algorithm for computer so that it knows how to approach this problem. So you guys need to think how we can communicate this to computer that it sells the given rod in maximum profit. Is that right, Raj?
Yes, yes, that's absolutely what we're supposed to do. And you can do it in two different ways. There's a recursive approach, and then there's a dynamic programming approach. So there's two different ways to do that.
Yeah. So Raj can cover a bit of recursive approach, and then I'll cover the dynamic programming approach. But the again, you guys need to first understand that when you see this problem for the first time, it does not say that it can be solved using dynamic programming, right? But how do you know that it can be solved using dynamic programming? That is because when I have that rod, which is 10 inches long, if I cut it in 1 inch, now I'm left with 9 inches. So me cutting the rod in 1 inch has affected the way rest of the 9 inches can be sold. Or if I make a cut of 2 inches, now I have 8 inches, right? If I make a cut of 4 inches, now I'm left with 6 inches. Making one choice is affecting the way I can make the other choice. So that's dynamic in nature. So probably this can be solved using dynamic programming. So probably you can use up 5-10 minutes of your time if you're given to solve this question for like 30-35 minutes. You can use up like 5 minutes to check what would be the time complexity if you solve this using dynamic programming. So Raj, can you please give like a brief idea of how it can be done using recursive?
Sure. So we can get the best price by making a cut at different positions and comparing the values obtained after the cut. So we can recursively call the same function for a piece obtained after a cut. What I mean to say, so for example, let's say the function is called cut rod and has one parameter n, and that's what gives us that function returns to us the best possible price for our rod of length n. So we need to recursively call cut rod with n so that we, by cutting it into smaller prizes. So let me get a screenshot of one possible way of how that is done. Let me share my screen just a moment. Oh, sorry, technical difficulty. There we go. Okay, so you can see this that in if this was the cut rod function and we want to call, and we have a number of prices in so we have I in 0 to n minus 1. So we have all the different pieces of n, and we want to calculate the value for all to get up to n. So we're going to take the max of the price of one small piece, and then we're going to cut the rod for the remainder of the piece. So for example, if I have a rod of length 10, and in my array I'm given one possibility as for the prices, one of the possibilities is for a small rod of length 2, the price is 5. So what I want to do is take price of I, that's going to be a loop. So you're going to take the price of the rod of length 2, which is 5, plus you're going to cut the rod for the remainder length. So you took a piece of rod of length 2, so you want to still find the maximum possible price for the rod of length 8, and that's what this function will do. It will generate, and if you loop through every single price that you're given in the array, you're going to generate all the possible outcomes and get the solution. So let me show you a piece of code that actually describes that better, and shows the whole solution. Okay, so here it is. This function cut rod, it takes an array of price and it takes the value n. We have a base case for the solution, that is when the length of the rod is 0, we just want to return 0. And we want to loop through and get for every possible. So we're taking, we get a max value because, that's the basic CS146 how to find the max. If you want to take the max value, we set one integer, that's the minimum, and then we keep updating it as we get a bigger value. So that max value is going to be the maximum price that we get. We recursively cut the rod in different pieces and compare the different configurations with this. So we run the loop from I equals 0 all the way up to the length of the rod. We say the max value is the maximum of the current max, or it's going to be the price of I plus the cost of cutting the rod of the remaining rod. So let's say we have a rod of length 8, and we have an array. Let me show that as well. So here's an example. In this, we're taking a rod of length array size. So that is 0, 1, 2, 3, 4, 5, 6, 7, 8. We have a rod of length 8, and these are the different prices for smaller pieces. And each smaller piece would be, so 1 for the rod of length 1, the price is 1. For the rod of length 2, the price is 5. For the rod of length 3, the price is 8. The rod of length 4, price is 9, and so on. And we basically loop through this array, and we get the configuration for each of it and recursively solve the solution. Shivanku, does that look correct?
Yeah, that looks absolutely on point. So that was an amazing explanation by Raj of how it can be done using recursion. And now I'll be explaining you guys how we can work our way through the dynamic programming way. So I'll just share my screen.
Shivanku,
Yeah.
just once before that, can I show why the recursion does not work well, and the recursion tree, and why the dynamic solution works better?
That would be the most perfect thing. Yeah.
Sure. Okay. So let me share another screenshot with you. Okay. So if you can see this if you can see the screen, in this particular example, we are trying to cut a rod of length 4, and going with the recursive solution that we just saw, we call the function on a rod of length 4, and then we have prices for rod of length 1, 2, 3. So we cut we get all possible combinations. So when we do a cut rod, we call the while we're doing for, we call it on 3, we call it on 2, we call it on 1, and we call it on 0, which is the base case. So when we call it on 3, we also call it on 2, 1, and 0. We also, when we call 2, we also call it on 1 and 0 there. But then when we call, when it finishes solving the rod for length 3, it comes back to check the next configuration. That is by taking the price of 2 and the remaining 2. We again, call the function on a rod of length 1 and 0. We go to the next. We move on to the next value in the array. That would be the price of rod of length 1. We again call it on 1 and 0. So you can see how we are repeatedly solving the rod for solving the problem for rod of length 0, for rod of length 1, for rod of length 2, and each time that we actually solve for rod of length 2 or 1 or 3, we can actually save these values. So once it has solved this portion, once it solves this whole piece, the rest of it is actually, when it comes back to this or this or this, it's just actually plugging the values in the table that we've stored already. Shivanku, do you want to go ahead and explain how we can actually put that into code?
Yeah, sure. So I'll show you guys the code as well as the way of working through. So so I hope my screen is visible, right? Yeah. So the way this thing, so as you guys saw, what in which Raj was the solution in which Raj was explaining, that there are multiple repetitions in the solution, and we can probably store those values somewhere, right? So how do we store those values is that we imagine that we want to obtain total length 0. Okay, I know it's a hypothetical situation, there is no length 0, but you start from the bottom and you reach till what your ideal aim was, or your target was. So let's assume that our target in this case was that we had a rod which was total length 4. So we will start by trying to make the total length 0, then we'll try to make the total length 1, then we'll try to make the total length 2, then 3, and then 4. By doing so, what we are doing is that we are trying to maximize the length 0, the way in which length 0 can be obtained using these pieces. Length 1 can be obtained using these pieces, 2, 3, and so on. So the last block, this one, the last block as a result of what we are doing will always be our answer. This is when we are following the bottom up approach. There is a top down approach as well, that we start solving from the other end of the spectrum and we reach the other end. But I always find the bottom up approach easier to visualize, and that's why I also recommend you guys to work your way through the bottom up approach, because it's easier for us to visualize something growing from 0 to the max, right? Rather than thinking the other way around, that because that's not the way human brain actually thinks. That's why if someone tells us to print a linked list, it's fine, but someone tells us to print a reverse linked list, we start to scratch our head, right? So what we need to do is, in dynamic programming, we try to avoid the base cases or the special corner conditions by taking some hypothetical values. So the first hypothetical value that we always take is that, one, we declare a new array in which we are going to store all these values. It can be a 1D array, it can be a 2D array. Okay. The second thing is that you initialize the first block in that 2D array to 0. Like in this case, I have initialized it to 0 in this column and this row, right? The third thing is that After you have initialized the stuff to 0, now you write your piece of code, and it's just, as I said, 1, 2, or maximum 5 lines of code, and you're done. I'll show you a piece of code is which I found out to be really logical and effective. So this Geeks for Geeks solution. You'll not understand it at the first go. I'm showing you just for reference. This is not exactly what how I'm trying to do it, but it's somewhat the same. Okay, so what they're trying to do is they are using a 1D array that can be done using a 1D array, but I'm using a 2D array. Okay, so I'll explain how they have also done. So you see, they have declared an array which is one size greater than n, because we want to accommodate the 0 as well. And then they have initialized the first position, which is the 0th position in an array, to 0. Okay, and then they have a new variable in which they are storing the maximum value, right? The maximum value. Okay, and this is the only important line of code in the whole 6 7 lines of code. And what this line is doing is, it says that it is taking max of two things. There's one value which is in which we were storing the maxes, right? And then it is trying to sum two things, right? So what it is doing is, it is taking the price of the piece that we are trying to sell plus the value of I minus jth column. Now let me jump into the PowerPoint and try to solve it with you guys. Okay, so if I am allowed, when I am in this cell, it means that I am only allowed 0 length of pieces, and I want to make the total length of 0. So the cost would be 0. Let's take prices so that we can solve this easily. Okay, let's take some virtual prices. So let's assume that I can sell rod 1 for $2, rod 1 for $2, rod 2 for $3, rod 3 for $5, and rod 4 for $4. Okay, so this is our pricing. This is our price matrix, price array you can call, which will tell us for how much I can solve the stuff. Okay, so now I am only allowed length of piece. So these represent the length of pieces that I am allowed, and this represents the total that I am trying to achieve. So I am allowed only 0, and I want to make it 0. Okay, that would be 0, right? So I am only allowed length 0, and I want to make 1. That's not even possible, right? Because I am only allowed the length of piece to be 0. So all these would be 0, right? This is our way of eliminating the edge cases or the boundary cases. Same would be the case here, that I am allowed a length of piece 1, but I want to make the total length 0. That I would, then I will not use it, right? So this would be 0, this would also be 0, and same, right? Now let's solve from this block and beyond, and you'll understand how we are trying to do it. Now I am allowed a length, piece of length 0 and 1, and I want to make the total length 1. Okay, so as we go, when I was here, I was only allowed a length of piece to be 0. When I came here, I'm allowed 0 and 1. When I will be here, I'll be allowed 0, 1, and 2, right? So I hope you guys are following what I'm trying to say. As I move down a column, the length of pieces allowed keeps on increasing, but the total length that I'm trying to achieve remains the same. When I'm trying to go along a row, the pieces that I'm allowed remains the same. I mean, if I'm traversing only in this row, then I'm only allowed 0, 1, and 2, but the total length that I'm trying to achieve keeps on increasing, right? So when I'm in this column, I'm allowed a pieces of I'm allowed a pieces of 0 and 1, and I want to achieve total length of 1. Okay, so that can be done using a piece of 1, right? I have a piece of 1, I want the total length 1, so I can make profit $2. Let me write 2. Okay, now I come to this cell. I am allowed 0, 1, and 2. Now I can take 2, and solve this one, right? So now let's write this. Now I am allowed 0, 1, 2, and I am trying to achieve total length 1. In this case, 2 doesn't make any sense because it is greater than the total length that I'm trying to achieve, right? So I'll probably not pick it. But here comes the interesting part. If I'll not pick 2, and let's assume I delete 2, isn't this the same condition as what I had already solved in the column above? It is, right? So I copy the same value in this cell, this value which was above, because it was the same. Okay, same would be the case when I come in this column. Now I am allowed 0, 1, 2, 3, but this is primarily the same problem as the previous one, because when we were allowed 0, 1, 2, I got 1. Now my problem states I can take 0, 1, 2, 3, right? And over here, 3 doesn't make any sense because my total length that I need to make is 1, right? So I'll not pick it. It's primarily same to my previous problem, right? So I can fill all 2's in this table, right? Now, if I am in this cell, now I want to make the total length 2 and I am allowed pieces 0 and 1, right? So as a human, I know that I need to take 2 pieces of length 1, right? So I need to take 1, it would be 1 plus 1, right? So it would be the cost of 1 was 2, the cost of 2 ones would be 4, right? So I can make a profit of 4. When I come in this column, this cell, it would be I am allowed a length of P0, 1 and 2, and now I come in this one, right? I can straight away sell the length of piece 2 for 2, right? But that would give me 3 as my profit. Whereas if I sell it in ones, I'll get profit as 4. So I'll keep on selling it for 4, right? And so on, when again you come here, since the value that we can take is lesser than the total length, we copy the same value in the columns below, right? So I hope you guys are trying, you are able to follow what I'm trying to say, that every time we are in the same column, we and the length of pieces which is allowed is greater than total length, we copy the same values, right? So we are doing two things over here. If you see clearly, we are, whenever we have to fill in a column, we compare it with the value which is above, right? And we compare it with the price of this piece plus something else, right? Because when I had to fill this one, I compared, okay, what's the price when I have to take 2 ones? It's 4, right? So I compared it this with the price of 2, which is 3, right? And I said, okay, it's 4. But what about this cell? Or what about this cell? So let's do this so that you can understand this one. So if I had to do total length of 3, I'll take 3 ones. That would be 2 plus 2 plus 2. That would be 6, right? And this would be 8. Let's solve this one. This is where the thing gets really interesting. Now I need to make total length of 3. I am allowed 0, 1, and 2, right? So there are a couple of ways in which this can be done, right? So let me remove all this. We are allowed 0, 1, 2, and we want to make total length 3, right? So I can either take all ones or I can take 1 and 2, right? So if I take, so this primarily means the column above, right? We have already calculated this one, and this one is something new, right? Okay, so the 3 ones is the 6. So our answer will be maximum. Our answer will be maximum of either 6, which was previous value, or sum of 1 and 2, right? sum of the column in which you are, right? So sum of the price of 2, you see, price of 2. So price of j, your value of j. So price of j, what's the price of j? Price of 2 is 3, right? So 3 plus, but how do I come to 1, right? The way in which you come to 1 is the way Geeks for Geeks was trying to explain you, that you do I minus j. Your ith value right now is 3 and your jth value is 2. So 3 minus 2 is 1. You look at the 1th value in the same row. 1th value in the same row is 2. And that's how you get 3 plus 2. So the maximum you can obtain in this case would be max of 6, 5. So even though the answer is maximized using ones, but it might very well have been maximized by the other way around, right? As well, right? I've taken such values that right now the maximum was obtained using all ones, but it is highly probable. In fact, when I was doing this in person, I took values which were higher, right? So these values can be anything. So this is how you work. So now if we look at the piece of code, you'll be able to understand it better. That it is telling you that take the max of the previous column or the price in which the price of the row, I mean the price of the rowth number in which you are plus the value which is stored at I minus j. It is taking -1 because it is dealing in a 1D array and it has stored 0 at the first place. So that is why it is taking -1. So now what they are trying to do, that also I can explain. Since we are trying to work with a 2D array, we are wasting a lot of space, right? And we can make it more space efficient by working through every row and then rewriting the results of every row, because ultimately we are only bothered with the last part of it, right? We are not bothered about all the other values, right? And when we are calculating something, we only need the values in that row as we need it by doing I minus j, right? So I can probably rewrite those values and obtain the result. So that is why their solution has just one array. Okay, so initially it's not easy to understand why they are doing that, but once you get a grip of how the 2D array is working, you can understand why and how it can be done using a single array. So I I hope this made some sense and you guys were able to follow up. So Raj, were you able to understand how rod cutting can be done using dynamic programming?
Yes, it's not the easiest. It is a little overwhelming, but I think the main key thing is that line of code that max val equals max of max val comma price of j plus, and if you see that that same line of code is was also the base of the recursive solution. So when you're thinking about a problem like this, if you're able to solve the problem using that, get that, or get that, that's the hardest part, getting that line of code. Once you have that, the rest of the problem gets a little easier. Sometimes, like Shivanku said, you could do it using a 2D array, you could do it using a single array. Any of those work. I think all programs can either be done using one or the other. The whole idea is to cache or save the solutions to the sub problem, so you can use them in the further problems.
Yeah, absolutely. I couldn't agree more with what Rajesh said, that that's the basic point about dynamic programming, that you store the intermediate values, you use them later on, and the first thing is you recognize that it's a DP problem, and then the main thing is that you realize that there are not a lot of lines of code that you need to write, right? And you are always maximizing or minimizing something. So you need to think how you can reach on those values in that table. That's it. And that is the key part. That is where you need to invest like 5 or 7 minutes thinking that, okay, is the statement through which I'm trying to obtain the max or the minimum value working accurately? Because if it is working accurately, it will hardly take you 5 minutes to code it. whereas if it's not working accurately, it will take you a lot of time. So that was it from our end for today. And for next virtual SI session, we'll probably cover some more dynamic programming problems, as well as we'll try to catch up or help you guys revise some of the stuff which was done in the start of the semester, because I know two of the midterms are going to come really quick for you guys, and the finals as well. So it will help you guys in having a quick glance over all the topics. So yeah, that's it. Anything you want to add, Raj?
No, I think just the next, we're going to continue having our regular SI sessions. So the next one's going to be on Tuesday at 1 p.m. Um, I will be covering dynamic programming, another kind of problem in that, and also doing some review of previous material. Please, please bring come to the SI sessions and bring your friends as well. It's better to wait, get start reviewing material now than wait right before the first road exam.
Yeah,
And that's all. I think you can leave the session now. Thank you for coming and joining us. We hope to see you at the next session.
yeah. Thank you. Bye.